Welcome to the Explainer. You've probably seen an AI do this. It reads a sentence and poof, it just knows who the person is, what the company is, or where the location is. It seriously feels like magic. Well, today, we're going to pull back the curtain on the clever little engineering trick that makes it all happen.
So, let's start by putting a powerful AI model to the test. The task is pretty simple. Just understand one single sentence.
All right, here's our sentence for today. My name is Sylvain, and I work at Hugging Face in Brooklyn. Super straightforward for us, right? You've got a name, a company, and a place.
And just like that, the model nails it. Sylvain is a person. Hugging Face is an organization. Brooklyn is a location. Perfect. It seems like it gets it, just like we do. But here's the kicker. The way the model sees this text is, well, it's not like how we see it at all.
You see, behind the curtain, the model isn't reading words. It's chopping everything up into these little pieces called tokens. So a name like Sylvain gets totally shattered into 4 different parts. And those double hashes you see, that's just a signal that these pieces are attached to the word before them.
So that's the big question, right? If the AI is just looking at this jumble of fragments, how in the world does it know to glue S, Helava, and Helene back together and realize, oh, that's all one name, Sylvain?
Well, the secret, the key to this whole thing, it all comes down to a really important difference between the tools that create these tokens.
So you've got 2 main players in this game. On one side, you have your slow tokenizers, usually written in Python. And then on the other side, you have the heavy hitters, the fast tokenizers, written in a super high-performance language called Rust.
And wow, this chart really shows you why they get the name fast. I mean, look at this. To process a huge chunk of text, the fast tokenizer does it in under 11 seconds. The slow one, almost 5 minutes. That's not just a little faster, that's a whole different league.
But here's the thing. Speed is awesome, but it's not even their coolest superpower. There's something else, a hidden feature that the fast ones have and the slow ones don't.
And that is what we're here to talk about. This is the superpower that lets the model follow that trail of digital breadcrumbs right back to the source.
It's a feature called offset mapping. And honestly, the best way to think about it is like this. As the tokenizer is dicing up the sentence, for every single tiny piece it creates, it leaves a little note, a little breadcrumb that says, hey, I came from exactly this spot in the original sentence.
So, step 1, just like we saw before, the tokenizer does its thing. It creates that list of tokens, breaking down a word like Sylvain into all its component parts.
Then, and this is clever, it assigns a word ID to each token. So all those little bits of Sylvain, the S, the hashtag Y, all of them, they all get the same team jersey, the same ID number. It's the first clue that they're all part of the same word.
And now for the secret sauce. This is it, the offsets. This is that perfect map we were talking about. Each token gets a pair of numbers that point to its exact start and end character in the original sentence. No guesswork, no kinda close, it's a precise GPS coordinate.
Okay, so with those 2 things, the word IDs telling us which tokens are on the same team, and the offsets giving us their exact location, we have everything we need. We can now solve the mystery. We can recreate the magic trick ourselves.
It really just boils down to a 4-step process. The model makes its prediction, right? It says, hey, I think these tokens are a person. Then we just look at the offsets for those tokens, and bam! We use those coordinates to go back to the original text and pull out the full name. Simple.
And you have no idea how important this is. Seriously, imagine trying to write code to piece home, hugging, and face back together. It'd be a total nightmare. You'd have all these weird rules and it would probably break the second you tried a different model.
But offsets, they just make it simple. It's this beautiful, universal solution. It doesn't care how a word got split up, the map back to the source is always perfect.
So let's take Hugging Face. It gets split into a few tokens, right? No problem. We just grab the starting number from the very first token's offset and the ending number from the very last token's offset. And voila, you've perfectly lassoed the original text Hugging Face. Done.
Okay, so this is a really neat technical trick. But why should you care? Why does offset mapping matter in the grand scheme of things?
Because this isn't just some clever little hack. It's actually fundamental to how these models work. It's what gives them their incredible precision, whether they're highlighting text or answering a complex question. It's the bridge, the solid connection between the model's weird chopped-up view of the world and our human-readable text. Without this kind of efficient, versatile solution, a lot of modern AI just wouldn't be possible.
It really gets you thinking, right? What other invisible superpowers, these elegant little engineering tricks, are hiding under the hood of the AI tools we're starting to use every single day? It's a reminder that behind all the magic, there's some really clever problem-solving going on.